Let's look now at the coefficient of variance. That's an A variance. All right, let's come up with a simple example here. Let's say we have grapes, and we have weighed them and determined that the average grape is about 6 grams, and we've calculated its standard deviation, and it's about 1 gram. And we have also weighed apples, and we say that they are about 80 grams, and their standard deviation is 20 grams. Okay. The question we want to ask here with the coefficient of variance is, in which group do we have the most variance, right? And in absolute terms, clearly the answer is apples, because there is 20 times more variation in apples than there are in grapes, right? But let's think in terms of that relative to our beginning point. If a person is 6 foot tall, plus or minus an inch isn't that big of a deal. But if you're only 3 feet tall, plus or minus 1 inch is huge. So it all comes back to, what was your base height, right? From where are you starting? And so when we want to compare something that have different starting points or different base heights, in the example we were looking at before, we call it the coefficient of variance. And it is equal to the standard deviation divided by the mean. So in this case, our coefficient of variance is 1/6. And in this case, it is 20/80ths, which reduces down to 1/4. Okay? So a couple of cool things have happened here. This is now a unitless measure, right? We had grams here and we had grams here, but they have canceled each other out because they were in the numerator and in the denominator, right? So now we have unitless measures, and we can compare 1/6 to 1/4, and we conclude again, just like we did before, that there is more variation inside the apples. But this is now a much more meaningful comparison, right? It wasn't 20 times as much. The example I can think of where this was done in an environmental study is they were looking at the reliability of precipitation in China. So they didn't want to know if in each location there was a lot of precipitation, if it was really wet or if it was really dry. They wanted to know, if you were a farmer there, how consistent was the precipitation? Could you rely on the amount of precipitation consistently across time? And so the measure for doing that was the coefficient of variance. All right, let's look at how to calculate the coefficient of variance in R. There's no function for that, but it's not that tough. We could create one. The coefficient of variance, where I have my input of x, is just the standard deviation of my x values divided by the mean of my x values, right? So as an example, let's open up the sample data set trees. We'll look at the dimensions of trees and look at the names of trees. So I'm highlighting all that. Since I use an Apple machine, I will hold down Command and hit Return. On a Windows machine, you hold down Control and hit R. But here I have created my function, which I've just called CV for coefficient of variance. I input x, and it returns the standard deviation of x divided by the mean of x. Here I'm opening up the sample data set trees. I have 31 observations and 3 variables, and those variables all are girth, height, and volume. So I could say, what is the coefficient of variance of trees' girth? So it's taking the girth variable from the trees data set and calculating the coefficient of variance of 0.237. I can also use the lapply command to calculate the coefficient of variance for all 3 simultaneously. So I have greater variability in volume, much less in height, so my trees were almost all the same height, and then moderate values there in girth. But so this is a way of comparing the variability, despite the fact that this was measured in inches, this was measured in feet, and I think this was measured in cubic yards. Despite the fact that they're all measured in different units, I now have a single value that I can use to compare them and say that there is more variability in volume than there was in any other variable.
Pretty straightforward.